This lesson deals with supplemental problem 222. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 49. We'll look at a little bit of nonlinear circuit theory. Suppose we put two nonlinear elements in parallel, shown here. What can we say about this interconnection? Voltage across at V is the same as the voltage across each element, and that the current entering here would equal to the currents that are leaving the node through elements 1 and 2. For the same voltage, you could add up the currents and get the overall VI characteristics of these two elements, knowing the VI characteristics of each of the individual ones. You can use that to find the VI characteristics of this circuit where I've got a diode D1, a 40 ohm resistor, and a 0.7 drop. And then in this direction, I've got a diode facing the other way, D2, with 17 ohms and a minus 10 volts. Let's sketch the VI characteristics of each of these series combinations. Start with the top one. If current begins to flow, then we have a 40 ohm resistor and a 0.7 volt drop. Let's take this diode to its transition point, where this current is 0 and this voltage across the ideal diode is 0. What's the voltage from here to here? Well, it's going to be 0 volts, but 0 current times 40 is 0, and then plus 0.7. I have this point right over here. If this voltage starts to increase, this becomes a short circuit. This is still 0.7, so any change in voltage would appear across this resistor. The change in voltage over the change in current would be 40 ohms. We're plotting current here and voltage here. The slope of this would be conductance, or 1 over 40 ohms. Let's see what happens when we have less than 0.7 volts. Well, let's solve for the voltage across here and see what it is. If this were off, the rise in voltage would be the voltage across here, and then that would equal V minus 0.7, and then we have no drop across here if this is an open circuit. Again, this voltage is equal to V minus 0.7. Whenever the voltage V is less than 0.7, then this is a negative number. So it's off. You have just no current flowing. Let's try the bottom element. Let's have the current flowing in here, and let's go to the transition point. So there's no voltage here and no current. No drop across here. Well, the voltage V would just be equal to minus 10 volts. That would be this point right over here. If we have an increase in current, this will be 10 volts, this will be a short. The change in voltage over the change in current would be the 17 ohms, but again, we're plotting a slope here of conductance, so it'll be 1 over 17. Let's solve for the voltage across here. When it's off, the rise in voltage is equal to drops around the loop. Rise in voltage is V sub D2. If I have no current flowing, there's 0 here. Minus 10 volts minus V. Whenever V is greater than minus 10 volts, we have no current flowing. So we have this VI characteristic set for these two elements. Now what we got to do is add up the currents for each voltage that's the same. Pick a voltage here. I have 0 plus 0 would be this. Over here I've got 0.7 plus 0, so 0.7, and then any increase in voltage would be causing the current to increase here, but this would still be 0. So you're just going to pick up this 1 over 40 ohms. And likewise in the opposite direction, as we get more and more negative, this is still 0, but now this begins to decrease with a slope of 1 over 17, and that would just continue because we're just going to add 0 to it. So what I've got is a forward biasing of 0.7 and a reverse biasing of minus 10. This would be a pretty good model for a 1N758 Zener diode, which you could find in the Motorola Semiconductor Data Library, Volume 1, Discrete Products, Series A on page 1-8. So we derived this VI characteristic by using a graphical analysis instead of a numerical analysis. And this is supplemental problem 222.